Okay. Good morning, guys. Almost ready to get started here. Today we're going to continue where we left off last time. You remember last time we talked about trigonometric integrals, section 7.2, and we learned how to handle powers of sine times powers of cosine. And well, it would be nice if that was all we needed. The truth of the matter is, we need a little more. Stock handling. This thing, please. Okay. Okay. We can look at one or two homework problems. Yeah, sure. If there are homework problems that you would like to look at, we can look at a few of them as kind of reminders of what we did last time. But if there's a large number of homework problems or a core concept from the homework that we want to spend time on, that would be better done in office hours. But yeah, just number 4. We could take a quick look at that. All right, so the main plan today is to continue section 7.2 by talking about the secant tangent integrals. But first, we can look at a homework problem. That's from homework 4, number 4. Homework 3, probably homework 4, right, Margaret? All right. Yeah, this is a little brutal. All right, this one's going to take a minute. We'll do it here. So we want to integrate 9 times the 4th power of cosine times the 2nd power of sine from 0 to pi. Like it is. So your numbers may change a little bit, but it should look something like this. It should be an even power of sine times an even power of cosine, and it should be a definite integral. Mouse pad can be moved here. Oh, there we go. The reason this problem is a bit of a hassle is because both of these powers are even. You guys remember what we're supposed to do in the case where both the power of sine and the power of cosine are even integers? Is our high-level strategy there. Yeah, we just bludgeon the thing to death with half-angle identities. We just smack it with those identities again and again and again until we get somewhere that we can finish the integral just using micro u subs. So the identities that we need are sine squared t equals 1/2 1 minus cos 2t, and cos squared t equals 1/2 1 plus cos 2t. We'll start with these. And you might be thinking, well, I don't have a cos squared t. We do. Cos to the 4 is cos squared squared. So my first step looks like this. All right, first I would write the cos to the 4 as the square of cos squared. And now I can go ahead and use both of those identities. And I popped out the 9 as well. So sine squared will get replaced by 1/2, 1 minus cos of 2t. And cos squared inside those parentheses will get replaced by 1/2, 1 plus cos 2t. So this is what my integral will look like. And I know it might seem like a hassle, but do be careful with your parentheses, right? When you're writing a trig function, always put the argument, the inside of the trig function, in parens, even if that means piling up like 3 stacks of parentheses here. It's worth it to make sure that your reader can tell what you're writing, and also to make sure that you handle the constants correctly. So I can pop out a 1/2. When I square all this stuff, that will give me a 1/4. So altogether, I'll be popping out 1/2 times 1/4 is 1/8. So this will become 9/8 integral 0 to pi 1 minus cos 2t. And this will be 1 plus cos 2t squared dt. My next step is going to be to deal with this power. I'm going to FOIL this thing out and then distribute this across it. So we're going to end up with a big long string of things involving powers of cos 2t. Let's see what that looks like. So again, I'm going to try to conserve space here. I don't necessarily suggest that you write this like I am, where I'm using like every little bit of space. You might want to just go line by line. This would be 1 minus cos 2t, I'll leave him. But then I'll FOIL this. This is going to be 1 plus 2 cos 2t plus cos squared of 2t dt, like that. Okay, and then we're going to distribute this over this. And you'll see that some of these things will be easy to deal with, some of them will not be super easy to deal with. We're actually going to get, this is kind of surprising to me, a cos cubed out of this as well. So 9/8 integral 0 to pi. When I distribute the 1, I'll just get this. And this piece here is going to need more half angle stuff. And then when I distribute the minus cos 2t, I'll have minus cos 2t minus 2 cos squared 2t minus cos cubed 2t. dt. So that's blowing the whole thing apart, right? Multiplying everything out, this is what we get. There are some common terms like this and this can be combined, this and this can be combined. So let's do that. So I'll have 1, and then cos 2t's. Got 2 of them here, minus 1 of them here, gives me 1 of them in total, so plus 1 copy of cos 2t. Cos squared 2t. Positive 1 of them here, minus 2 of them there, gives me minus 1 of them overall. And then, no more, and then cos cubed. I've just got 1 of those. Okay, so we're almost there. Remember, the kind of philosophy here is that we beat these things to death with the trig identities until all the powers are gone, right? This is still an even power, so he's going to get mo half angle. This odd power, this is interesting, he's going to get some special treatment. He's going to be treated according to the rules for the odd powers. So this guy we're going to kind of have to think about differently. I'm probably going to end up treating him as cos squared times cos, and then doing a little bit of u sub. But first, let me go ahead and do the further half angle stuff here. So remember, since cos squared of t is 1/2 1 plus cos 2t, cos squared of 2t is 1/2 times 1 plus cos of 4t. So far, I'll put the identities I've used in my little boxes. This is the modified half angle formula. We talked about this a little bit last time. You just replace t by 2t in this expression, and you get this. And this will let me get rid of this power. The cos cubed, I'm gonna, like I said, I'll deal with him separately. So here's what I'm gonna get just from this step. Minus 1/2 1 plus cosine of 4t. And I'll go ahead and peel off the cos cubed here. So we'll have minus 9/8 integral 0 to pi cos cubed of 2t dt. Because he's an odd power, he's going to need separate techniques from the rest of this stuff, which is looking like the normal even powered routine. So now I can distribute my 1/2 here, combine the like terms, and then do any micro u sub work, and this piece will be done. This piece, trying to see if there are any symmetry arguments we can make to let him go faster. I don't think there are, so we just got to deal with it. Well, yeah, you might be able to make a symmetry argument here because cos of 2t is periodic with period pi. So you're integrating cosine cubed over a full period. Maybe there's a trick there, but I think we're going to have to just go with it. So from here, when I distribute this 1/2, I'll have 1 plus the cosine of 2t minus 1/2 minus 1/2 cos 4t. And this guy right here, I'm going to rewrite him thinking about u sub as cos squared 2t times cos 2t. And then to this piece, I'm going to apply a Pythagorean identity. So no doubt, this is a long problem. The even powers are kind of the nasty cases in the sine cosine integrals. And here, the total power is 6, right? You've got a 2 and a 4, so you can expect that this will take a little bit of work. If I put this 1 and this minus 1/2 together, those are both constants. That'll give me a positive 1/2. And then I'll have plus cos 2t minus 1/2 cos 4t. Oh shit, I've been leaving my dt's off. Somebody slapped me in the face. There we go. All right, this is pretty much done now. Happy with this. I can integrate this using micro U subs and everybody's good. This guy is nowhere near done. I'm going to replace cos squared 2t by 1 minus sine squared 2t using the Pythagorean identity. All right. So here I made use of the identity cos squared theta equals 1 minus sine squared theta. To rewrite cos squared 2t as 1 minus sine squared 2t. (9/8). Yeah, so the 9 was out front at the very beginning, and then a 1/8 came out from our identity work in the first line. So those are 9/8. All right, let me go ahead and do the antiderivative step on the first integral. That'll be 1/2 t plus sine 2t over 2. And that's a micro U sub, minus, I've got 1/2 cos 4t. Cos 4t will integrate to sine 4t over 4, so that'll be sine 4t over 8. And that gets evaluated from 0 to pi. And then I've still got this piece over here. In this piece, I want to make a substitution. I want to substitute for sine of 2t. Maybe for now, I'll just write it. I'm just going to copy the integral down. Because I'm following the algorithm for the odd powers, right? Where if you have an odd powered function, you should grab one copy of it and set it aside with a differential, and then try to substitute for the other. So after I set this cos 2t to the side, I knew I wanted to substitute for sine of 2t. I didn't have any sines of 2t, but I knew that that was what my algorithm told me to do. So I went ahead and rewrote the remaining 2 powers as sines. So now I'll make the substitution here. Z equals sine of 2t. dz is 2 cos 2t dt. And when t is equal to 0, z is equal to 2 times, z is equal to the sine of 2 times 0. The sine of 2 times 0 is 0. It's the sine of 0. When t is equal to pi, z is equal to the sine of 2 pi, which is also 0. So as I suspected, this son of a bitch isn't going to contribute anything. And it would be nice if there was a way we could have seen that sooner, but I don't see an obvious explanation for it. But I hope that you're seeing from here, because these bounds both map to each other, we're not going to get anything out of the second integral. The reason I was able to tell a priori that this was going to be 0 is because cos cubed goes through a full period, because this is cos cubed of 2t. So it'll spend as much time above the x-axis as he does below. And that's what we're seeing here. When both of these bounds come out to 0, this integral is going to be 0. But I'll go ahead and pretend like it isn't. I'll pretend like I can't tell that it's going to be 0. And just for fun, we'll get to see what it looks like. The evaluation step here is similarly trivial, because sine 2t and sine 4t, when you plug in either of these bounds, they're 0. So this first piece is really just going to be 1/2 times pi. Everything else is 0. Then we have minus 9/8, and I'm going to write it as silly as it looks, the integral from 0 to 0, 1 minus z squared, and then my differential cos 2t dt, that's 1/2 of dz, so I'd get a 1/2 dz here, just to show you how that substitution looks. But of course, because the integral is running from 0 to 0, this whole thing is also 0. So altogether, right, because the integral from a to a of any function is always 0. This piece is going to be 0. And here, when we plugged in the bound pi, here I got 1/2 times pi plus 0 minus 0. And then when I plug in the bound 0, I get 0 plus 0 minus 0. So the whole thing is just this. So at the end of the day, we get 9/8 times pi over 2, which is 9 pi over 16. And that's the game. So this is definitely a longer problem, harder problem. Still quite tractable, and if you follow the rules from last time, you'll get there eventually. You just have to be patient. Questions on any one of these steps? Of course. Yeah, it's a neat problem. It is. It's definitely a little bit of a pain in the ass. This kind of gives you a feel for the worst case, right? How unpleasant can the sine cosine integrals get? This is about there, right? This is about as long and tedious as one of those could get. And it's pretty long and tedious. So here's the first few steps. We started by writing cos to the 4 as cos squared squared, and then drop in our half angle identities. Then we FOIL and distribute. Then on this piece, which is still an even power, we use our modified half angle identity. Distribute. And I broke off the cos cubed integral at this step because he's not an even power, he's an odd power. So he's going to get different treatment, right? Even powers and odd powers, different treatment. The odd powered guy, if we were really clever, we could have stopped here and said this is going to be 0. But you'd have to know what the graph of cos cubed 2t looks like. And I don't know if everybody in this class can picture the graph of cos cubed 2t. I don't know if I could have pictured it when I was in Calc 2. But without the cube, remember what cos 2t looks like? It looks like cos t just smushed in by a factor of 2. So from 0 to pi, cos of 2t spends the exact same amount of time above the x-axis as it does below the x-axis. And cubing him doesn't change that. So if we were sufficiently clever, we could make a geometry argument at this stage saying that this piece is 0. But if we don't see that, then we just continue with the normal rules for the odd powers. And over here, I was distributing the 1/2, combining like terms, and then micro u subs finish the job. This is a t. All right, so your numbers may change a little bit, your answers may change a little bit. I caution you strongly against asking a problem and then just putting the answer that I give you in. If you do that, then you're definitely not getting what you should be getting out of the homework. The point of the homework is definitely to struggle with these a little bit. In Calc 2 and certainly other math classes in your future, you're meant to struggle and have those moments at 10 p.m. in the shower where you go, oh yeah, You know, that sort of shit. So I don't want to steal those moments from you. I want to make sure that you still spend time and have those moments. As long as you're getting to those moments, eventually you're in good shape. It's okay to feel like something is difficult. But I want to continue where we left off last time now. So we're going to continue section 7.2. As promised, with integrals of the form secant to some power times tangent to some other power. Again, the reason that we're breaking down into powers of sines and cosines and powers of secants and tangents is because if you're given a combination of basic trig functions, multiplied, added up, as long as the insides are all just x or theta or whatever, no constants multiplying inside, then you can always split those up and rearrange them into powers of secant times powers of tangent, plus or minus powers of sine times powers of cosine. And some of your homework problems require you to go through that splitting up process before you can dig in. But it's an interesting fact that you can do that. It's not hard to prove. I think the best way to get started here is with some examples that sort of showcase the technique we need. So I'm going to start with something easy here, like tangent x times secant squared x dx. Let me make this tangent squared. All right, so we just spent some time sifting through an integral where both of the powers were even and it kind of sucked, but those were sine cosine integrals. Here it's a secant tangent integral. Does anybody see anything that we could do to this? We could rewrite either tangent squared or secant squared using the Pythagorean identities, that's true. Remember, tangent squared, that's secant squared minus 1. And so secant squared, that's 1 plus tangent squared. We could do that. But I think there's an even easier path. Think u sub. What sort of substitutions could we make here? Yeah, the derivative of tangent is secant squared. We don't want to rewrite as sines over cosines because we want to learn how to tackle these sort of integrals as they are. But if you remember that the derivative of tangent is secant squared, then this is ready to go with a substitution for tangent. And you should ask yourself why this substitution works so nicely. So tan squared, that'll be z squared. Secant squared x dx, that's exactly dz. So this is super simple. This is 1/3 z cubed plus c, which is 1/3 tan cubed or tan cubed over 3. Plus c. And then my question to you is, what made this so nice? Why were we able to do this? And the answer is because I had a secant squared here, right? Because the power of secant was even. If the power of secant is even, then you can always grab off a secant squared to make this substitution go through. What's more, if the power of secant is large and even, then after you grab two of them off, what would be left over is even and could be rewritten in terms of tangent. So let me jack this power up a little bit. I'll play with the tangent power a little bit too. How about tan cubed x times secant to the 4x dx? Could I do the same thing? Yeah. So I'll grab two of those secants. And set them aside with the differential. So if the power of secant is even, one attack is to take two of the secants and set them with the differential. And that means we're thinking about substituting for tangent. So everything else has to be rewritten as tangents. That first piece is okay, but this piece, he needs a little bit of love. So here I would use my identity tan squared plus 1 equals secant squared. So I'll have my tan cubed x here. Secant squared I rewrite as tan squared x plus 1. And then the last secant squared is still chilling. Here I've made use of the identity. That's the second Pythagorean identity. I used this on this. Now if I substitute for tangent, again, everything will go nice and smooth. So what's making these work is the fact that the power of secant is even. If the power of secant is even, you can try to substitute for tangent. You take two of the secants and set them over with the differential, and the remaining secants you rewrite using your Pythagorean identities. So this is z to the 5 plus z to the 3 dz, and that is 1/6 z to the 6 plus 1/4 z to the 4 plus c, and then finally that is the 6th power of tangent over 6 plus the 4th power of tangent over 4 plus c. So I'll do one more example like this, which I'll annotate with the strategies on the right. Questions on either of these? Does anyone see another way this integral could be done? Does anyone see another substitution we could try? I'll give you a hint. There's another way to do this one, but there is not another way to do this one. What gives me the possibility to do this one with a different substitution is the fact that the power of tangent is odd. I could take one copy of tangent and one copy of secant. I could put a secant tangent to the side, and then I would have tan squared times secant cubed times secant tangent. And the tan squared I could rewrite in terms of secant, and then substitute for secant. So those are the two main strategies for secant tangent integrals. You're either going to try to substitute for tangent, which means setting two secants aside, or you're going to try to substitute for secant, which would mean setting a secant and a tangent aside. First, let me do one more example where I outline the strategy. So, if the power of secant is even, so I'll make this I'll make this like this, so there's only one possible attack here. Then our first step set aside 2 copies of secant with the differential and then we're going to rewrite the remaining secants as tangents. We do this thinking about little sub for tangent, because the derivative of tangent is secant squared. But then I need to get whatever's left over rewritten as tangent. So secant squared, that's tan squared plus 1. So the second step there is to rewrite the remaining secants as tangents using the second Pythagorean identity. So when I set aside 2 of these, because the power was originally even, when I set aside 2 of them, I'll have an even power left. And that even power of secant can always be rewritten in terms of tangent using that Pythagorean identity. Which means now we're ready to substitute for tangent. That's our third step. And when I do that here, I'll have z to the 4 times z squared plus 1 times dz. So this will always yield a polynomial. And polynomials are easy to integrate. This is z to the 6 plus z to the 4 which has as its antiderivative z to the 7 over 7 plus z to the 5 over 5 plus c, which is 10 to the 7 over 7 plus 10 to the 5 plus c. So if the power of secant is even, this is your strategy. First, set aside 2 secants with the differential, thinking about substituting for tangent. Then rewrite the remaining secants as tangents using the second Pythagorean identity, which is that secant squared x is tan squared x plus 1. And then you go ahead and make the substitution for tangent. So this would be z to the 4. This would be z squared plus 1. And secant squared x dx is exactly dz. So anytime the power of secant is even, this works great. Questions on the strategy here? Okay. So the other nice case is if the power of tangent is odd. So I could have something like tan cubed times secant, secant to the 4. Something like this. Oh wait, I wanted to do something that doesn't fall into the other category. Let's do tan cubed secant cubed. Sorry. So there the power of secant was even. We could have done that the other way. What you're going to see is that there's overlap between these cases, right? You could have an odd power of tangent and an even power of secant, and those integrals could be done either way. But for this example, I want to give you one that can only be done according to this rule. So if the power of tangent is odd, we're going to do something else. I'm going to start by setting aside a copy of secant times tangent. So that will leave me tan squared here, secant squared here, and then secant x, tangent x dx. So your first step here is to set aside a copy of secant tangent with the differential. Why do I do that? Because that's the derivative of secant. I'm thinking about substituting for secant. Then we need to rewrite the remaining tangents as secants. So tan squared is equal to secant squared minus 1. So your second step is to rewrite the remaining tangents as secants using, again, the second Pythagorean identity. That's what we've done here. After setting aside one secant and one tangent, I have two tangents left over. Because the power of tangent was odd, this will always result in an even power of tangent, which can always be rewritten using that identity. And now you go ahead and make the substitution. Now we're going to sub z equals secant x. dz then is secant x times tangent x dx. So your third step here is to sub for secant. This will always yield a polynomial. And again, polynomials are easy to integrate. So here I'll have z squared minus 1 times z squared times dz, which integrate, I can distribute them. So that's z to the 4 minus z squared. Which has antiderivative z to the 5 over 5 minus c cubed over 3 plus a constant, which is secant to the 5 over 5 minus secant cubed over 3 plus a constant. So the two cases, the cases we considered for the sine cosine integrals are different than the cases we consider for the secant tangent integrals. Power of tangent being odd, or the power of secant being even, those are the two nice cases where you can get away with u sub. It's just a matter of setting aside the appropriate amount for substitution with the differential, and then using trig identities to rework the rest of the material into what would be a polynomial when you make that substitution. Unfortunately, these two cases are not exhaustive. It's possible that the power of tangent isn't odd, and that the power of secant isn't even. And that's the bad case. So first, questions on this integral? Just like with the sine cosine integrals, there is an overlap case, right? Sine cosine, if both the powers were odd, you had a choice. In the secant tangent integrals, if the power of tangent is odd and the power of secant is even, then you have a choice. You could attack either way. And it's up to you to determine which way you want to do. Again, my advice would be to try substituting for the larger power. So if you've got like tangent to the 2021 times secant squared, or secant to the 4, then you should want to substitute for tangent, which would mean setting aside 2 secants. If you had like tan cubed times secant to the 2020, then you should want to substitute for secant. Okay. Let's look at the nasty case. Yeah, exactly. So if the power of tangent is even, and the power of secant is odd, then put on big boy pants. Try some IBP. Cross your fingers. Basically. These can be handled. They're just a little bit rough, and like Maggie said in chat, these are similar to the secant cubed integral. Remember the secant cubed integral we discussed last week when we were talking about integration by parts as an example of a looping integral. And in the secant cubed integral, you do have an odd power of secant and an even power of tangent. The even power of tangent there is 0. Let's look at another example like that. So I'll do 2 of these. Secant times tangent squared. One option is to rewrite tangent squared as secant squared minus 1. And then that will give you a secant cubed integral. Another option is to jump in with some IBP. I could pick u, so I can think of this as secant x tangent x times tangent x dx. And if I pick this to be u and this to be dv, then I can at least fill out my IVP table without too much trouble because I know how to integrate secant tangent. That's as much logic as I'm putting into it, right? How can I split this up into something I know how to integrate times something I know how to differentiate? I know how to integrate secant tangent, and I know how to differentiate tangent. Secant tangent is the derivative of secant, so the integral of secant tangent is secant. And the derivative of tangent is secant squared. So you can probably see a secant cubed hiding in here too, right? So we'll get u times v, which is tan x times secant x minus the integral of v times du. V times du is secant x times secant squared x dx, which is secant cubed. But my goal is to make the integral loop. So I could from here say, oh, I know what the integral of secant cubed is, and plug that in if you happen to have that memorized, but I don't expect you to. I certainly didn't in Calc 2. But what I do see here is potential to make this integral show back up. How could I get secant times tangent squared out of this? Well, secant is secant, but I know secant squared can be rewritten as tan squared plus 1. So now I use the identity. Secant squared equals tan squared plus 1. So these are like a puzzle, right? You need to think about them really hard and see how you can make your original integral show back up. You're still going to have an integral of secant left over to contend with. I'm just going to distribute. So this will be minus integral of secant x times tan squared x minus dx, sorry, minus the integral of secant x dx. Does everybody see that? I distribute this secant, and I'll get secant times tan squared plus secant. And then I distribute this minus. So I'll have minus integral of secant times tangent squared minus the integral of secant. And this is my original integral. So now we have looped. So my next line, I would write therefore integral secant x tan squared x dx equals tangent x times secant x minus the integral of secant x times tan squared x, and then minus the integral of secant. Do we know what the integral of secant is? This is one that we should commit to memory. It's the natural log of secant x plus tangent x. This piece right here being this piece right there. So now if I add this, oh shit, I'm leaving off my dx's. I'm so sorry, guys. This is not a habit I usually get into. If I add this to both sides, I'll get 2 times the integral of secant x tan squared x dx equals tangent x times secant x minus the natural log of secant x plus tangent x And at this stage, I'll start writing my plus c's because I have no more integrals on the right-hand side, and then divide by 2. The divide by 2 I'll write as multiply by 1/2. And you don't have to divide the c by 2. So we need to distribute this negative. All right. So you distribute the secant, you get secant times tangent squared plus secant, but then you also distribute this negative. So that's why both of these are negative. This actually looks very similar to the secant cubed integral. I don't know if you remember, if you swap this minus for a plus, you get the secant cubed integral. So they are quite similar. And this business of being very careful distributing negatives, we've seen a few times in integration by parts, can be a little bit of a stumbling block. It's an easy place to make a mistake. So if you want to take an extra line between here and here to write out exactly what this is the integral of secant times tangent squared plus the integral of secant, and then distribute the negative, then you'll see that both of these come out negative. Okay. So yeah, this is the rough case. The tabular method can make looping integrals a little bit easier. If you like the tabular method, again, it's not an official part of the curriculum here at Santa Fe, but if you want to Google it, some of these problems I do tabularly when I have to do them on my own. Okay, how are we doing on time? 9 o'clock. We have 15 minutes. What would you guys like to do? I've got two options. I can start introducing the material for next week, which is a little bit early to be doing that since it is only Wednesday, or we could take a look at another problem or two from this chapter, this section. Are there other problems like this that you would like to see? Yeah, more examples? Do we want to do sine, cosine, or secant, tangent? Are there any particular problems you guys would like to look at? Secant, tangent problems? You want to do looping ones or the guys like we were looking at the start? I got you. All right. So for these to be looping integrals again, they have to fall into that category. The power of secant is odd. The power of tangent is even. We just did secant times tangent squared. The next natural one to look at would be secant cubed times tangent squared. So the move again is going to be IBP. I need to choose how to split this into U times dV. I could, let's see. Could grab a secant tangent, and that would leave me with a secant squared times tangent. Or I could grab a secant squared, and that would leave me with secant times tangent squared. Those are both quite hard. Let's see. So you pretty quickly wander down, you run into stuff that is tricky. So let me try this two different ways. Let me try this as secant squared x times tangent x times secant tangent. So I could make this u and this dv, or I could make this u and this dv. Let's try it like this first. Let's call this u and call this dv and see where we get. It's not going to be pretty. Again, the way I'm choosing to split u and dv is I'm just trying to pick for dv something I know how to integrate quickly. So the integral of secant tangent is secant. The derivative here, the du, is going to be nasty as all hell. It's going to require the product rule. So let's give it a shot. If I differentiate secant squared and leave tangent alone, I'll get 2 secant x times secant tangent and then times tangent plus, leave secant squared alone, differentiate tangent, that's secant to the 4, or secant squared times secant squared. So that's what du looks like in that case. Is this absolute hell? Kinda. So what is this? This is 2 secant squared tangent squared. Plus secant to the 4 so u times v minus the integral of this times this, the powers of secant will all go up 1. We can give it a try. I'm gonna need more space on it. All right, so that's u times v, that's a secant squared tangent times secant, that's secant cubed times tangent minus the integral of v, which is secant times du. So that's multiplying du by secant is just going to bump all the powers of secant up by 1. So that'll be 2 secant cubed x times tan squared x. Ooh, that's good news. Plus secant to the 5x. That's bad news. Dx. Why is that bad news? Because the integral of secant to the 5th is a bitch. You can run IBP on this once and reduce it to the integral of secant cubed. But let me just show you how this would work. So we get secant cubed x tangent x minus 2 integral secant cubed x tangent squared x minus integral secant to the 5th x dx. And now it is true that my integral has looped. But it ain't pretty. And I still need to integrate secant to the 5th to finish the job. So I'll recap this. Secant, integral secant cubed tangent squared is equal to secant cubed times tangent minus 2 integral secant cubed tangent squared dx minus integral secant to the 5x dx. And now I can add this over. So I'll get 3 copies of integral secant cubed x tangent squared x dx equals secant cubed x tangent x minus the integral of secant to the fifth of x dx. So when we do these looping integrals with odd powers of secant, usually we end up with just the integral of secant here. And we know that. That's not a hard integral. That's the natural log of secant plus tangent. But this time I end up with an integral of secant to the fifth. I don't know that. But we did make our integral loop, and so I could divide by 3. But before I do that, I need to evaluate the integral of secant to the fifth, which is more IBP. So you see how these get nasty, right? If we wanted to proceed from here, I would take the secant to the fifth and split it as secant squared times secant cubed. Set up my IBP. And I would have to run IBP twice on this to reduce it down to an integral of secant. Not easy. So we think, maybe I should try the other attack. Maybe I should try splitting this in some other way. I could split it as secant squared times secant tangent squared. Or I could try swapping u and dv here, because the integral of this isn't too bad. But I think because the combined power here is 5, this integral is basically equivalent to the secant to the fifth integral, which is necessarily nasty. So you can see that there's no free lunch here. These are just hard. I'll show you what the IBP setup looks like for the integral of secant to the fifth. So we can try to finish this. I could take u to be secant cubed and dv to be secant squared. Or if I'm feeling really sneaky here, I guess the fast way to do this would be u is secant squared x and dv is secant cubed x dx. Then the dv to v step is nasty. Du here would be 2 secant x times secant tangent. So that's 2 secant squared x times tangent x. And then the integral of secant cubed I happen to have memorized is 1/2 secant x tangent x plus the natural log of secant x plus tangent x. So I'm actually hiding a looping integral in the dv to v step here, because the integral of secant cubed all on its own is a bitch. So we'd have u times v minus the integral of v times du. Ooh, that's not nice. So I'll pop the 1/2 out. When I multiply this times this, no. This is horrific. Okay, this ain't the way to do it. I'm gonna stop here. So, the point of this is that these are friggin' hard. We can get through it. The secant to the fifth integral here, I thought maybe I could find a sneaky fast path by tucking secant cubed in the dv to v step, but then in the resulting integral, we would have to integrate the product of these two things, which would be secant to the third times tangent squared, that sucks, plus secant squared tangent times the natural log of secant plus tangent. Good luck. Good luck. So this is not going to work out like this. If we wanted to do this, we would have to try some other attack on the secant to the fifth integral. Maybe splitting it the other way would work. But no matter what you do, this is going to be horrific. So the take-home message here is that if the power of secant is odd and the power of tangent is even, well, yeah, like I said before, put on your big boy pants, cross your fingers. It's tough. These are tough. And the combined powers kind of tell you how tough they will be. So here the combined power is 3 plus 2 is 5. So it's necessarily going to be a long problem. I think there's no way to get through this without doing at least 3 loops. So at least 2 IVPs. There may be a more clever way to set this up at the start, but if I'm honest, I'm not sure what it is. And I've been doing this shit for years, guys. We could take this to be, we could take secant squared to be dv. I'll try one more way, but I don't want to burn time on things that I'm not going to make you do. And this is certainly an example of something I would not make you do. So I could try u and dv chosen as, what did I do last time? Secant tangent there. So I could do secant squared. Is there a way I could make the dv to v step soak up as much as possible without ruining things? I could do secant squared times tangent. I think this is probably the nicest way I can think of to do this. And then u, what would u be then? The secant tangent. Yeah, so here's trying with u and dv chosen the other way. V here is going to come from a little u sub. I would substitute for tangent. It's focused, focus. Right. So to pass from v to dv, I need to integrate secant squared times tangent. The way I would do that is by substituting z equals tan x. dz would then be secant squared x. So it would be z squared over 2, or 1/2 tan squared x. And du, I have to differentiate this. This does require the product rule again. So if I differentiate the secant and leave the tangent alone, derivative of secant is secant tangent, that would be secant x times tan squared x plus, I leave the secant alone, I differentiate the tangent, I get secant squared times secant, which is secant cubed. So I would have this dx. So that's the alternate IBP attack here. And then my u times v is going to be 1/2 secant x times tan cubed x minus the integral of v du, 1/2 tan squared x times secant x tan squared x plus secant cubed x dx, and we can hope for something nice. You'll see that I will get my loop. When I hit this tan squared with this secant cubed, I will have my loop. The question is, what's left over? Is what's left over manageable? I would have secant times tangent to the 4. And again, the power of secant is odd, the power of tangent is even, so that would be rough. But I'll show you what the loop looks like again. We'll see if we can manage it. So this will be 1/2 secant x tan cubed x minus 1/2 integral secant x tan to the 4x dx minus 1/2 integral tan squared secant cubed, or secant cubed tan squared. I'm thinking that there's probably no getting around needing a second IBP here. This might be a little bit easier to handle than secant to the 5th, but not really. But if we loop then, I'll have integral secant cubed x tan squared x equals 1/2 secant tan cubed minus 1/2 integral secant tan 4 minus 1/2 integral secant cubed tan squared. And I can add this over, and I'll get 3/2 integral secant cubed x tan squared x dx equals 1/2 secant x tan cubed x minus 1/2 secant x tan to the 4x dx. But again, after a single loop, I'm still left with a very, very challenging integral. So what can we do with that? Is that any easier to manage? The truth is that this integral on its own is a looping integral, just like the secant cubed and secant to the 5th integrals. So really, there's no nice way to do this, guys. That's the upshot. I'm not even sure it's worth the time. If we wanted to try and proceed from here, we would set up another integration by parts. I think the move would probably be to do it similarly to what we did here in the previous. So I'd take 2 of the tangents. Oh no, I don't. Yeah, I can't do that. So I'd take a secant tangent and make that my dv. And then tan cubed would be my u. But he on his own is going to require coming to the side and doing a looping integral. So I think I'm going to abandon ship on this one, honestly. I would rank this as being far too hard for Calc 2. And if I wanted to give you a clean path to a solution here, I don't actually encounter these on the regular, but the easiest way to handle these, I think if you're like really stuck and you really must and you don't see anything clean, is to just make them odd powers of secant. So tan squared, I write that as secant squared plus 1. So this is secant cubed times, secant squared minus 1, which would be the integral of secant to the 5th minus secant cubed. And then you got to go through the IBP. This is going to be 2 runs of IBP, each involving a loop. This is 1 run of IBP involving a loop. It's hard, okay? Hard with a capital H. So I am going to abandon ship on this example, but I hope that seeing that work kind of gives you an idea for how you would handle these in general. Let me scale it back. So we did secant times tangent squared, right? We've done secant cubed on its own. I'm not sure there's much else that's really accessible here. Everything else is going to be, frankly, really friggin' hard. I can see if there are any other examples like this in the textbook, but as soon as the combined power gets over 5, you're in real trouble. So let's see, are there any other examples like this that I'm not aware of? Yeah, no, that's easy. Easy. Nope. What about in here? Even odds. no, 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 no. This one we've done, tan squared times secant. Yeah, no, and for good reason, because as those powers get larger and larger, these things really do get out of control. So there is something in here that I would like to show you though. Do they do the reduction formula stuff? Well, they don't. They don't do that in this book, huh? Okay, yeah, you guys are safe. So the other examples where the power of tangent is even and the power of secant is odd aren't present in the textbook because they're so goddamn hard. So I wouldn't slap you with anything out of control like the last example we tried, and I don't have any others on hand in my mind because frankly, when you encounter them, the mathematician's approach is going to be to break them down into odd powers of secant, and then odd powers of secant do kind of follow a pattern. There's something called a reduction formula that you can prove. One run of IBP on this will turn him into some shit, and then the integral of secant cubed, I'd glom the two secant cubes together, and then run IBP on that. But it's not at all simple. So what I want you guys to focus on are the manageable cases. And I think we might have time for one more of those. Oh no, we're way over time. All right, so don't stress about the horrible case here where the power of secant is odd and the power of tangent is even. Make sure you know how to integrate secant cubed. Make sure you can integrate like secant times tangent squared. But don't worry about like secant cubed times tangent squared. Put your effort into the cases that aren't so bad, the U sub cases. Make sure you can handle those. Those make good exam problems, and that's about the appropriate level for this class. Ratcheting the difficulty up on these looping integrals really isn't fair to you guys. I would need about an hour to get through this on my own, and so I certainly couldn't ask you guys to do that on a test or anything. I got to get running to my other class right now, but I do have an office hour this afternoon. If anybody wants to come by and chat problems, I'll be there. Otherwise, you can send me messages on Canvas. I'll be going through WebAssign trying to clear extension requests, but hopefully everybody's caught up with that stuff. If you're not, please get in there, get that previous homework done. That way we can move forward. Next time, I'm going to introduce trig sub. So I'm sorry that the last few minutes of class here kind of devolved. Trig sub is where you take an integral that doesn't have trig functions and you make a substitution that forces trig functions into it. That might sound like a nightmare thing to do, but there are many, many problems that can only be solved using trig sub. And for some reason, this is a big sticking point. I think because it involves some work with inverse trig. So brush up on your trig skills, right? Hopefully going through 7.2 is doing that for you, but make sure you also remember the inverse trig functions, their derivatives, and their domains. Make sure you can evaluate inverse trig functions using the unit circle, all that stuff. And that's where we will go next time, okay? I gotta go ahead and sign out. I hope you guys have a lovely rest of your day, and I will see you either in office hours or on Friday.